So before we get into entanglement quantification, let's look at what we did in lecture number 24. So lecture number 24 was about verifying entanglement, and there are two generic ways for verifying entanglement. One is through EPR correlation measurements, and the other one is through demonstration of Bell's inequality violation. EPR correlation measurements, we found that it is suitable for verifying entanglement in continuous variable systems, while demonstration of Bell inequality violations, this is suitable for verifying entanglement in finite dimensional systems. So we saw that EPR correlation measurement basically amounts to verifying this relation experimentally, or measuring this relation and demonstrating it experimentally. And we presented several experiments in which people had measured this quantity and shown it to be smaller than h bar by 2, and thus verified entanglement. So this was done. This type of verification have been experimentally demonstrated in position momentum, for entanglement in time and energy, for entanglement in angle and orbital angular momentum. Bell's inequality violation, on the other hand, is used for demonstrating entanglement in the polarization degree of freedom. It can also be used for demonstrating entanglement in the continuous variable system, but by making a 2D state space out of this continuous variable, and thereby making a 2-qubit state just like this, and then doing a Bell violation and thus verifying entanglement. So Bell inequality violation can also be used to verify entanglement in this continuous variable system, but by making a 2-qubit state or a two-dimensional state space out of these variables. So these are the two generic ways of verifying entanglement. But now today we want to do entanglement quantification. Just a few facts first. So Bell inequality violations and EPR uncertainty measurements, these verify the presence of entanglement. They do not quantify entanglement present in a quantum state. The field of entanglement quantification is a very active area of research, but still at this point we know how to uniquely quantify entanglement only of the 2-qubit state. I mean, one knows how to quantify entanglement of a generic 2-qubit state. Of course, if it's a 2-qubit state and if it's a pure state, then one knows how to quantify entanglement. For the generic 2-qubit state, we don't know. So as far as generic states are concerned, at this point one knows how to uniquely quantify entanglement only of 2-qubit states. So no unique quantifier of entanglement for multi-particle d-dimensional quantum states. So let's now we'll get into what are these entanglement quantifier and how to use them. But before that, I'll go through the some basics of 1-particle and 2-particle quantum states, and then some math related to these 1-particle and 2-particle quantum states, so that we are familiar with the terms used in entanglement quantification. This is just the basics. So when we say pure state, like a 1-particle pure state, we mean that a 1-particle pure state can be represented as a column vector, the dimensionality of which is the dimensionality of the Hilbert space in which the system lives. So an n-dimensional, for example, if the Hilbert space is n-dimensional, then a 1-particle state, pure state, we can write it in this manner. So the summation over n, I to n, and then the phi I is the basis states, and di, that's the coefficient. For example, if you have a 2-dimensional state, we can write it as psi equal to alpha 0 plus beta 1, where 0 and 1, these are the basis states. This 0 we can call it h or v, ket h or ket v, or ket 0 or ket 1. The ket 0 can have a matrix representation in the 2D basis as 1 0, ket 1 can have basis matrix representation as 0 1. So together we can write it as alpha beta. So this state psi in 2 dimension, these are all equivalent representation, alpha 0 beta 1, or like this, or just writing as a column vector with alpha and beta. Of course, alpha square plus beta square, that has to equal to 1 for the normalization. So that's how we represent a 2-dimensional 1-particle pure state, and this is how we represent an n-dimensional 1-particle pure state. Just to have an example of a pure state, we discussed this already. Suppose we have a laser with an H horizontally polarized photon coming in. If it goes through a beam splitter, it splits the possibility of the photon going into two. So either the photon can go this way or the photon can go this way. Let's put a half-wave plate so that this turns if the photon comes this way and become horizontally polarized, then after passing through the half-wave plate, it will become vertically polarized. So the state right after the second beam splitter is essentially alpha H plus beta V, where alpha and beta are the splitting coefficients and depends on the reflection of the mirrors and so on. But the state right after this beam splitter is alpha H plus beta V. And this we can represent as just alpha beta, just like we did it over here. So that's the coherent superposition, and this is what's called a pure state, one particle pure state. Of course, when alpha beta is equal to 1 over root 2, we have psi is equal to 1 over root 2 H plus V, and that's a 45-degree polarized light. So that's an example of a two-dimensional one particle pure state. Okay, now let's look at what's one particle mixed state. So when a one particle system cannot be described as a single ensemble of realizations and has to be described as a mixture of ensembles, then the one particle state is said to be a mixed state. So an n-dimensional version of a one particle mixed state would be that we have this psi is just then the symbolic representation of the state. So if we can take this one for example, and then we take the ensemble average of the psi and that becomes the n-dimensional one particle mixed state. And we can write this like this, where di dj, although it started from here, and we are now taking the ensemble average of di dj star. A two-dimensional version of this would be that we have this double summation. It goes from 1 to 2 di dj psi I psi j. We can write this as a two-dimensional one particle pure state. This is like d1 d1 star, d2 d2 star, d1 d2 star, d2 d1 star. So that's a generic two-dimensional one particle mixed state. So of course, when this determinant of rho is 0, that's when it becomes a pure state. An example of a pure state could be here, this psi that we have, this we can write as a rho, that's a density matrix, and then the representation is alpha square, alpha beta star, and beta alpha star. So psi equal to alpha beta and rho equal to this. These are equivalent representation. At least for pure state, either we can write it as psi equal to alpha beta, or we can write it as rho like this, and we can see that here the determinant is 0. So this does not contain any more information than this representation contains. So for a pure state, this one, that one, this one, this one, these are all equivalent representation. But when we do have a mixed state, then of course this is not just a product of alpha and beta, then it will have an ensemble average here, and that's what makes the difference between a pure state and a mixed state. So that's the one particle mixed state. Now one particle mixed state can be represented as a mixture of pure state. So for example, this rho, if we do, we can always find a basis. For example, this psi is in this phi I basis, but we can always find a basis in which this rho actually can be represented as a mixture of pure state, or in fact the rho can become diagonal. So this rho, we can always find a basis states in which rho can be written as a product of a mixture of pure state, like in this manner, where of course this individual density matrices are of the pure state. Now when this mixture contains only one term, then it is of course a pure state. So at this point, I just want to kind of remind that what we are doing here is pretty similar to what we did while doing the classical coherence part. So there we saw the density matrix elements in quantum description and the correlation function within classical description play analogous roles. So this we had discussed. And also the representation of a mixed state density matrix as a sum of pure state density matrices is same as the coherent mode representation of correlation function. So earlier we had done this coherent mode representation of correlation function, and so what we are doing here for density matrix is same as the coherent mode representation we did for the correlation function. So just to refresh our memories, so this is the coherent mode representation we had done in the polarization basis. So in the polarization basis, we wrote the polarization matrix like this in the xy basis. Then we said we can find a basis x prime y prime in which this becomes diagonal. That means in this basis we can write this j as a sum of pure states. So that means a times this quantity, a2 times this quantity. Now this is essentially a pure state representing horizontally polarized light, or rather x prime polarized light, and this a2 times this state, which is a y prime polarized light. This coherent mode representation is the coherent mode representation here, or the representing a mixed state as a mixture of pure state, or when we do the diagonalization of a matrix, these are all one and the same thing. These all involve diagonalization of a matrix, and these are all one and the same thing. So what we do here is basically, this is the one particle density matrix, and writing it as a mixture of pure state essentially involves diagonalizing this matrix, which is the same thing that happens in this coherent mode representation as well. So that's the connection I wanted to kind of point out. Now, to give an example, again we have done this before, to give an example as to what is a one particle mixed state. So we can imagine a laser number 1, laser number 2, these two lasers. These are two independent lasers, and we have a photon either coming from this or coming from that. We don't have two photons, so we are in a situation where we have photon either coming from this or coming from that. And if the photon comes from this, it is horizontally polarized. Photon comes from this, it is vertically polarized. And if we mix this two at the beam splitter, then the state right after the beam splitter, we cannot write this state as alpha H plus beta V. This is because this is not a coherent superposition, because there is no phase correlation between this laser and that laser. So the state that comes right after the beam splitter, we can only write this as a density matrix, and then density matrix containing a mixture of pure state, this H state, and this pure state, that is a vertically polarized photon. So this is a mixture. What comes out here is not a coherent superposition of horizontally and vertically polarized light. It is rather a mixture of horizontally and vertically polarized light. So that's an incoherent superposition, and in such situation we have to have the density matrix representation because it is a mixed state. Now of course, when alpha beta is equal to 1 over root 2, this rho is half HH, half VV. So that means 50% horizontally polarized light, 50% vertically polarized light in the mixture, and that gives us the unpolarized light, as opposed to 45-degree polarized light. That's what happens when we have a coherent superposition. So that's the representation of a one particle mixed state. Now let's go to the two particles. So we want to see what do we mean by a pure state of two particle, and similarly a mixed state of two particles, and so on. So the concept is exactly similar as we have for one particle. So for two particle, a two particle pure state can be written as, let's say in one dimensional system like this. This is a two dimensional summation. So some dij phi ia, this tensor product phi j b. A refers to the first system or first particle, and B refers to the second particle. And phi I, that's the basis states for the first particle, and phi j, that's the basis states for phi j b, that's the basis states for the second particle. Okay. Now this, sometimes we don't write this tensor product over here. So either this or this, these are two equivalent representations. So first ket is for the first particle, second ket is for the second particle. If we have a two-dimensional state, then one example of such a state could be alpha HH, beta HV, gamma VH plus delta VV. So this H is the basis, HV is the basis state for single particle, but HH, HV, VH, VV, these are the two particle basis states. And where we have this H, the first ket corresponds to the first particle, second ket corresponds to the second particle. And if we write this in the ket form, we write it like alpha, beta, gamma, delta. So here I just want to kind of do a quick introduction of how we understand tensor product, which is what we are doing here or there or there. So when writing a two particle basis states, we can write it as a tensor product of individual particle states. So suppose we have H, that is 1 0, and V, that is 0 1. This is a two-dimensional space. That's also a two-dimensional space. So then the two particle basis state can be written as HA tensor HB. So that's the basis state corresponding to the first particle, which we call A, and HB is the basis state corresponding to the second particle. Of course, this is horizontally polarized, so we need not write A and B, we can just write H tensor H. We can also just write it as HH. So these are the different notations that is used in the quantum information text. So these are all equivalent ways of writing it. So first ket is always first particle, second ket is always second particle. So if we have the convention, then we don't explicitly need to write A or B. And again, when we write this tensor product is kind of implied. So even if you don't write, it is assumed that it is a tensor product. So now HH, the tensor product, how do we write? So this H is 1 0, the tensor 1 0. The way we do it is essentially we multiply this A, multiply this 1 by this column and the 0 by this column. So this 1 times this column, 0 times this column. So this essentially becomes 1 0 0 0. So that's the representation of HH. That's a two particle basis state. The individual particle basis states are this, and so the 2 particle basis state becomes this. So if it's HV, this was HH, so if we take HV, we can write it as, we don't need to write AB, so we can write like this or like that. These are all equivalent representations, and in that case we have 1 0 tensor 0 1. So this is an 1 0 coming over here, then we multiply each with 0 1 0 1, and so it becomes 0 1 0 0. This 0 multiplying with 1 gives us a 0. So that's the 2 particle state HH, and this one is the 2 particle state HV. So that's how we calculate the tensor product. In fact, we also have, even for the 1 particle state, we have these quantities like HV or HH we have for the like projectors. They're also although we call direct product, this direct product and tensor product in this context are the same thing. So this is also a product, and we calculate it the same way. So this is 1 0 for H, and V will be this, if this is a ket, so that's a column, this is a bra vector, so that's a row, so it's 1 0 0 1. So again we do 1 0 and multiply this with the row here 0 1 0 1, and so that becomes 0 1 times 0 0, because 0 multiplied with 1 is essentially 0. So that's the HV. So either we can write it like that or write it like that. These are 2 equivalent things. And if you have HH, so these are the projectors we do when we do measurements. In that case, we can see that it is 1 0 0 0. So this is just a quick introduction to tensor product, because when we write a 2 particle state, this tensor product is what we mean. And when we write a projector, either 1 particle, when we write a 2 particle projector, then it will be HH HH. There also what is implied is the tensor product, and that's how we calculate it. Okay, so now let's look at an example of a 2 particle pure state. In fact, this we had seen in the context of Bell inequality discussions. So here is a scheme in which we have a 45-degree polarized pump photon coming in. So 45-degree polarized pump photon is essentially a coherent superposition of horizontally and vertically polarized light. So we have now 2 parametric down conversion crystal. The first crystal is arranged with such a phase matching condition that if a vertically polarized light comes in, it produces 2 horizontally polarized light. The second crystal is arranged in such a way that if we have a horizontally polarized light coming in, then it produces 2 vertically polarized light. So a 45-degree polarized light has a 50% chance of being vertical, 50% chance of being horizontal. So if it comes here, it produces 2 horizontally polarized light, this term. If it gets down converted here, it produces 2 vertical. This would be this would be VV, a vertically polarized light here. And since the single photon is in coherent superposition state, the 2 particle state that it produces, that will also be in a coherent superposition state, and hence this is 2 particle pure state. Okay, now let's look at what we mean by 2 particle mixed state. So when a 2 particle system can be described only as a mixture containing ensembles of different 2 particle pure states, then we call it a mixed 2 particle state. So in an n-dimensional space, the 2 particle mixed state can be written as in this manner, where we have this A of course corresponds to the first particle, B is to the second particle, phi IA the basis states for the first particle, phi JB are the basis states for the second particle, and these are the ensemble averages. In a 2-dimensional state, we can write this as just this IJ, these summation only, this is only go up to 2, that's a 2-dimensional space. And if we write it explicitly, so the 2 particle 2-dimensional state, mixed state can be written like this, where we have all these are just the ensemble averages. So that's a 4 by 4 density matrix. Of course, when we have this 2-dimensional 2 particle state, pure state, that's just a 4-dimensional column vector, but this is a 4 by 4 density matrix with which we can represent a 2-dimensional 2 particle mixed state, that's a generic state. If the determinant of this rho is 0, then of course rho represents a pure state. Now just like 1 particle state, a 2 particle mixed state can also always be represented as a mixture of 2 particle pure state. So we can write it like this summation, where psi k are this rho k, which are the individual pure state. When this mixture contains only one term, that's a pure state, that's a 2 particle pure state. So this math works exactly the same as we do for 1 particle. It's just that we have to have we do this in a 4-dimensional space rather than a 2-dimensional space. So for example of a 2 particle mixed state, suppose we have this 2 particle state HH, and this HH, that's the density matrix representation of a 2 particle pure state. in which both the particles are horizontally polarized. V, that's the density matrix representation of a two particle pure state in which both the particles are vertically polarized. And so if that's a pure state, that's a pure state. If you put them together as a mixture, that becomes a two particle mixed state. P1 plus P2 of course has to equal to 1, and if we represent that in a density matrix form in the HH, HV, VH, VV basis, that's a 4 basis state for the two particle two dimensional state, then the matrix would look like this. All the other terms are here are 0. So that's an example of a two particle mixed state. Of course, how do we produce such a thing? So one way could be that, let's say we have a pump photon and it comes and produces an HH. We have another pump photon, it comes and produces a VV, and then we put them together. Now, since there is no phase correlation between these two pumps, what we will get is that, of course, this pump produces a pure state HH, this pump produces, this down conversion produces a pump state VV, but we'll essentially have the mixture of these two, and hence this would be a two particle mixed state. So this is how we understand a two particle pure state and mixed state, which is very similar to the concept we have for one particle pure state and mixed state. Okay, now that we know about the pure and mixed state, let's look at entanglement quantification as to how it is done. Now, the entanglement of two particles, it is not about whether the two particle state is pure or mixed, it is about the inseparability of the two particle state. So, if the joint state of the two particles cannot be written as a product of these states of the individual particles, then the two particle state is said to be inseparable. The degree of inseparability, that actually quantifies the amount of entanglement. And if a two particle state is separable, then of course the degree of inseparability and thus the entanglement is 0. So there are several different ways of quantifying the degree of inseparability and thus the entanglement. We'll look at one particular way, which is called entanglement of formation, and that has been worked out for a generic two particle qubit state, and that's what we will review as to how it is done. So we have a two particle pure state. Let's first define the entanglement of formation for a two particle pure state. So a two particle pure state, in general we can write it like this. This is in n dimensional, here we have written. Now such a state can be can always be written in a what's called the Schmidt decomposed form. So here we have a two dimensional summation here. This two dimensional summation can always be written like a one dimensional summation. Of course, we'll have to find a new basis. Here it is phi I corresponding to the phi I A corresponding to the first particle, phi J B corresponding to the second particle. We'll have to find another basis, phi I tilde A and phi I tilde B, in which this will have this Schmidt decomposed form. Of course, the Ci squared, that needs to be equal to 1. So entanglement, once we have this decomposition, the entanglement of formation of pure state, pure two particle state is defined like this. This is E, that is the entanglement of formation of psi, this state, and this is minus sum over Ci square log Ci square. So that's the entanglement of formation. So how this Schmidt decomposition is actually done, I will actually not go through it. One can go through some references for this, but since we will derive one formula that's for the generic two particle state, and that's what we are going to use in this course. So this I will not get into the actual how actually Schmidt modes are derived, but this can in principle be done. So in just one example, a few examples to kind of explain Schmidt decomposition. So suppose we have a two particle state in the two dimensional space like this, HH, HV, VH, VV. So this can actually be written like this. This can be verified. So it's H plus V root 2 tensor H plus 2V by 5. Now this is just a single summation. So in this Schmidt decomposed form, we have a summation, but here we find that this can be written just as a single term. So we have C1 equal to 1 and C2 equal to 0. So the entanglement of formation here is minus 1 log 1, which is 0. And this is what we would expect, because here this two particle pure state we have been able to write as a product state. So that's a separable state, and hence separable state the entanglement is 0. So this is unentangled. Let's take another example. Again, a two particle pure state in this form, alpha HH plus beta VV, where alpha square plus beta square is equal to 1. Now the Schmidt decomposed form, this itself is the Schmidt decomposed form for this one. So for this one, C1 equal to alpha, C2 equal to beta. So the entanglement of formation here is minus alpha square log alpha square minus beta square log beta square. Of course, this is not equal to 0. So that this is entanglement. And we can see that this state cannot be written as a product state, and hence it is inseparable, and hence it will have finite entanglement. So when C1 is 1 over root 2 and C2 is 1 over root 2, we have alpha, when alpha is 1 over root 2 and beta is 1 over root 2, then the entanglement of formation is 1, and that's the maximally entangled pure state of two particles in two dimension. So that's how we calculate entanglement of formation, although it is, it is definitely defined for even n dimensional state, two particle, not just for the two dimensional. But now let's look at how we do it for the entanglement of formation of mixed state. So let's first, we recognize that a two particle mixed state can always be written as a mixture of two particle pure state. And here when we say this, we mean it's more like in n dimensional space, and that's a unique representation in the sense of diagonalization. But and again, these different psi i's are orthogonal to each other. But if we do not have the restriction of the psi i's being orthogonal, then it is no longer unique. There can be many more such a representation, that two particle mixed state. There can be several different ways of writing that as a mixture of two particle pure state. Of course, this m will be different than n, need not be equal. So at entanglement of formation of mixed state, that is defined like using this quantity. So of course we have the definition only for the pure state. So when we write that in a mixed state as a mixture of pure state with weightage Pj, this rho j is the individual pure state. So this is the entanglement of formation of rho j times the weightage, and this is for this particular decomposition. But again, there can be several such decomposition. This diagonal one is one unique such representation, but there can be several such. So the entanglement formation of mixed state is defined as that we take all of these possible decomposition, we calculate the entanglement of formation on all of those decomposition in this way, and whichever is the minimum, that becomes the entanglement of formation of the mixed state. So this is a minimization problem that is involved here, and this is indeed a very difficult problem. But this minimization problem has been solved for a two particle two dimensional state, that's a 2 qubit state. And then this has been done in terms of what's called the concurrence. This is done by William Booters in 1998, and this is a very, very nice and useful formula. This is almost given, this minimization has been given in terms of almost a formula, and it goes like this. So for a two particle mixed state rho, we construct this rho tilde density matrix, which is sigma y times sigma y, this rho star, sigma y is a Pauli matrix. After that, we construct this rho tilde. We find the eigenvalues of rho tilde, arrange them in the descending order. Let's say lambda 1, lambda 2, lambda 3, lambda 4. Lambda 1 is the largest eigenvalue, lambda 4 is the smallest. And the concurrence of the mixed state is then defined as the maximum of this quantity, which is 0, and under root lambda 1 minus under root lambda 2 minus under root lambda 3 minus under root lambda 4. So either this quantity or whichever is the maximum of 0 or of this one. So concurrence cannot be, of course, less than 0. So this is defined as the, of course, the concurrence, this is just a new term defined, but the concurrence here has a direct relation with what's called the entanglement of formation. But now, in fact, this is the quantity that is being used mostly for quantifying entanglement of two particle two dimensional state, and it is this quantity. So in fact, this quantity we can also use for two particle pure state, but this is for two particle two dimensional state. This is the generic formula. So we have the entanglement quantification for general two particle n dimensional state, and if it is pure, and that is in terms of entanglement of formation. But for a two particle mixed state, if it's more than 2 dimensions, we don't know how to do this minimization problem. But this has been done for the two particle two dimensional state, that's a 2 qubit state, and for that 2 qubit state, the entanglement of the concurrence can just be found using this formula. In fact, this stays between 0 and 1. That's the 1 is the maximally entangled state, 0 is no entanglement. So that's how we do the entanglement quantification, and this is how much we can use in this course. Of course, this is a very intense field of entanglement quantification, and of course I have covered only a tiny part of that. So for this lecture we will stop here. Thank you.